Today I'm going to talk about the new generation of the solar cells, which is basically and physically is not based on photovoltaic effect at all. So it's different kind of solar cells, and in our proposed cell, because there are some nonlinear optical effects, so we call this kind of solar cell nonlinear optical solar cells. So just I will review the basic physics idea of the photovoltaic cells. Physically, it doesn't matter if you have the organic kind of the photovoltaic cells or if you have a semiconductor photovoltaic cells. In both cases, the basic physics is the same. The energy of the light and the energy of the photon will be absorbed by the active material. Electron-hole pair is generated inside the active material, and by dissociation, the electron-hole pair in the output circuit, you will get the current. This kind of photovoltaic effect is basically limited by the Shockley cell limits. It's for the single junction cells is 32%, and if you were in the morning talks, is all the different methodologies are going to work to go and efficiencies beyond these limitations. About 3 decades ago, a new kinds of idea for the solar cell came to the bench of the research, which call it RECTENNA. So what does this RECTENNA mean? RECTENNA means that you will harvest the energy of the light by harvesting the wave, electromagnetic wave of the light. So it doesn't work with the energy of the photons at all. It just uses an antenna, like the antenna that we use in the broadcasting to harvest the signals of the waves of the signals. Here we use an antenna to harvest the electromagnetic wave of the light, and then to get the power, the DC power, we need a diode or we need a rectifier to get the actual power. So this RECTENNA configuration is working well in the radio frequency to transferring the power, but for optical frequency to work, we should pass some limitations. But these kinds of the solar cells is theoretically can go to the 85% of efficiency. So compared to 32%, it's a high differences. The two challenges is, first, we need a nano-antenna scaling size to harvest the electromagnetic wave of the light, and it should work at the optical frequencies. And the second part, it means that we need a rectifier which will work at this high frequency. With actually, the traditional diodes will not work at this high frequency. So for first of the challenge, what we can say is that the question is that, is it like that simple, we get an antenna and shrink to the nano size and then catch the light? The answer is that no, we need to recalculate everything for that size, because when we go to the optical regimes, two different phenomena are working to harvest the light. First is the antenna methodologies, and the second is the plasmonic effects, which is working at the optical frequencies. So considering these two methodologies, we should recalculate the length that is needed to harvest the wavelength of the light, which will be shorter than the actual length that is in the classical calculation for the optical length. But if we got the correct length of the antenna, we can harvest all the harmonics of a wavelength, and through the different lengths of the antenna, we can harvest all the spectrum of the light, basically. And is this area of the nano-antenna is available? The answer is yes, because of the different technologies in nanofabrication, now having area of a nano-antenna is possible. The second part is that we need a rectifier which work at this high frequency. So to solve this challenge, in our group, Dr. Nanzi proposed an idea to use an optical rectifier. So what does this mean? If we consider the polarization inside the material, in linear regime, the polarization is dependent to incident electric field linearly. But if we have an intense electric field and in nonlinear media, we will have the polarization which is related to different powers of the incident electric fields, and we have different order of nonlinearities. The optical rectification that I proposed is, I said is the second order nonlinearities. Maybe most of you have heard about second harmonic generation, which is the same order of the nonlinearities. At the same time, when we have the second harmonic generations, it means that we have the frequency as double frequency of the input incident light. At the same time, we have another component which is omega minus omega frequency, which means that it has zero frequency and it is an static polarization. So what does this visually mean? If I show the second harmonic generation, if you have a nonlinear media, for example, you have an incident light at red, you will get output of twice frequency, which will be in the blue region. So this is second harmonic generation. At the same time, in the same material, we can get the optical rectification. To sense the optical rectification, which is a static polarization, you need the capacitor configuration, because these static polarizations make some bounded static charges at this interface of the electrodes. So if we made a capacitor configuration, we can sense this voltage, which is coming and which is related to this second order nonlinearity or second order susceptibility and incident electric field to the power of 2. To sense these kinds of phenomena, optical rectification, we need a correct tool. So I started with some preliminary tests on the materials that I was sure that the other students got second harmonic generation from. So I made the cells array of the silver nanoparticles on top of the ITO. This is an AFM image. Maybe it's not showing clearly the nanoparticles that I will have, but after I got the spectrum and after annealing the samples, it shows that I have the nanoparticles there. Previous student worked on this and get the second harmonic generation. So theoretically, I could have seen the optical rectification of these kinds of cells. So I made capacitor configuration based on that array of the silver nanoparticles using a polymer spacer. I made this kind of capacitor, and I test these cells using a femtosecond lasers and using the mechanical chopper and locking amplifier to sense. Now this signal is a very low-level signal. It's a nonlinear phenomenon, so low-level signal. So I need this configuration to sense this low-level signal. To investigate the output results, and that I will show to you, and to be sure that the output voltage is coming from the second order nonlinearity, not other phenomena, we should know more about the second order tensor at these cells, which due to symmetries that we will have on this kind of cell, we see that just 3 non-zero components in the second order tensor will be available, and we just care about these 3 components in different directions. So the results, the output results showing about 1 to 3 microvolt output voltage coming from the cells, and versus different polarization of the incident light. If we change the linearly polarization or circular polarization, we will see the changes in the output signal, which shows that versus the tensor components that I told you, it shows that by sure this coming from optical rectification is not coming from some effects like multi-photon absorption, because I have done some similar tests to see multi-photon absorption, which are different nonlinearities but shows different changes versus the polarization of the incident light. The next step will be, then now I have a tool that I can go through the real optical rectification. The next step is that I will make this array of nano-antenna. I will make array of nano-antenna through using the electrochemical deposition process, and I will grow this array of maybe gold nano-antenna through the anodized aluminum oxide pores, and the results shows that from this structure I can benefit from the plasmonic resonance. I mean, this structure is kind of the metamaterial. So I can benefit from the plasmonic resonances in this structure, which shows a large absorption at the resonance frequencies. And totally, I will say that if we want to have this cell to work quantitatively, it means that if we need the electrons comes out of this cell. So I need a voltage which is comparable to the oxidation potential of the molecules at top of the area of nano-antenna, which is around 1 volt. I need at top of the nano-antenna. So detailed calculation shows that if I consider the intensity enhancement, intensity concentrations by concentrated photovoltaics, and consider the effect of the plasmonic enhancement, which shows about 10 to the power of 7 intensity enhancement in experiments like surface enhanced Raman spectroscopy, and multiple all these by the enhancement that I will get through the Chi2, which is the second order susceptibility, that this second order susceptibility also will be enhanced through this structure because of the length of the nano-antenna. Totally, I will get voltage differences which is more than 1 volt at top of the area of nano-antenna, which is more than enough to ionize the molecules and get electrons out of the cells. So the proposed final cell will have a symmetric forms of 2 arrays of nano-antenna with the molecular rectifier attached at top of the antenna, and we need a electrolyte in between this to transfer the charges. Yeah, we will work on it, but it will come soon. Finally, I want to thank my group at Queen's University, Dr. Nanzi's research group there, and the funds which are coming from PV Network and CERC. Thank you.